So today we're talking about range filters, but before, let's just acknowledge today's the last lecture. So thank you for a really nice semester. This was a really fun class for me. Thank you for making classes very engaging and yeah, being willing to discuss. Okay, so first of all, let's just remind ourselves what is a filter. So, we've seen this many times throughout the course. A filter is this compact probabilistic data structure that answers approximate set membership queries. If we have a bunch of keys in a set, we can ask whether a given key exists. And the filter, right, the filter can tell us yes or no. So these filters are quite useful. Right? We can put them in main memory, and then by asking the filter whether something exists, we can avoid accessing storage, which is much slower. That saves us a lot of performance. Okay, and here are the semantics. So the filter ideally returns a negative, right? That's the best case scenario, in which case we don't actually have to search storage, but it could return a false positive with a probability epsilon, or it returns a true negative with a probability 1 minus epsilon. Okay, so we saw filters are very useful, but now what happens if we want to support a range query? So what do I mean by this? All the filters we've seen so far answer a query for whether a given key exists. In this lecture, we want to ask, what if we want to query for a whole range of keys, everything in between A and B, and we want the filter to tell us whether that range is empty or not, right? Because if the filter can tell us that the range is empty, we don't have to go to storage, and that can save us a lot of performance. But if the range, if at least one key in the range does exist, we do want the filter to return a positive, because then we want to find at least the one key or potentially more keys that are within the range to return the correct output to the user. Okay, so here's an example. Here we're asking, this is a range query between 3 and 5, and the answer to that should be a true positive because 4 is in the set. All right, and here's another example of a query from 5 to 8. Where this range actually happens to be empty in the key set. So in this case, we would get right, a true negative with this probability, but we could also get a false positive with this probability. Okay, that's what we would want at least. Okay, so what are the applications for this? Why do we actually want these? Well, the killer application for this are LSM trees. Right, so in LSM trees, you have your data stored across multiple runs in storage, and you potentially have to search multiple of these to be able to find, your result set. Now all LSM trees that we know of in practice actually use point queries. That means that whenever you're issuing a range query, however small that range query is, you still have to search every single level. So your performance is proportional to the number of levels, and that's not ideal, right? So because of that, right, so ideally, we want to have range filters there to allow us to skip runs that don't contain the relevant key range. Okay, and it's actually LSM trees that I think caused range filters to kind of break into mainstream research. This has been a very active area of research over the past 10 years. And that's precisely because of LSM trees. Okay, so let's get into the question of how to implement a range filter. And first of all, I want to discuss, as usual, some strawman solutions to the problem. So why not just take a point filter and, like a Bloom filter or a quotient filter, right? And try to use that as a range filter. So, so what can go wrong? So suppose that now I'm querying from everything between 5 and 8, right? And I have this filter here. Well, first of all, how would I actually process a range query using this filter? This is the natural approach, right? I can actually try to query for every single key in the target key range. Okay? So that's possible. And if that's what we're going to do, right, then if every single one of these queries returns a negative, then we know for sure that nothing in the key range exists. But if at least one of these queries returns a positive, then the overall range query has to return a positive as well, because there might be at least one key. So this would be how the semantics would work. Okay, but this is going to have a bunch of problems. Okay, so first of all, any questions about the strawman solution and how that works? Okay, so what are the problems with this? Okay, so I see two hands. Other hands? Hongcheng?
It's obviously going to be slower in CPU, have a higher CPU cost.
Yeah.
And this works if the key is discrete.
Yes.
The continuous key might do something too.
Excellent. So those are two problems. There's actually one more problem. So,
False positive rate.
yeah, why? Correct. Yeah, so the false positive rate is going to go up as well because we have to issue a lot more queries. And the chance that at least one of these queries returns a positive is, pretty high if you're issuing quite a lot of queries. Okay, so let's actually look at those overheads in a bit more detail, right? So our query cost is not going to be proportional to R, the range size. Not ideal, especially if you want to, if there's a large range. Secondly, this does not work for an infinite universe of keys, right? So this only works for fixed length keys. So imagine that you have strings. Well, the issue with strings is that you can actually have an infinite range, right? In between any two keys, you can have an infinite number of keys in between. So this just doesn't work with infinite keys. Lastly, higher false positive rate. So let's break this down. Okay, so we can analyze this, and I think it's just a nice exercise to actually show how you analyze this. So what's the probability of a false positive? Well, that's going to be the probability that at least one of the queries that we issue returns a positive, one of the R queries. That in turn will be 1 minus the probability that all queries return a negative, right? Now take that and say, transform this probability into the probability that one of the queries returns a negative, but raise that to the power of R because that's the number of times you're repeating that experiment, right? And then, right, the probability of one query returning a negative, that's just this by definition for a given filter. And then given some identities that we've actually seen in the course, right, you can simplify this into this. This is a good approximation. And then if you want to use the union bound, you can actually kind of upper bound the whole thing by just epsilon to times R, right? What this is saying, right, the union bound tells us that, the probability of at least one event of a set of events happening is upper bounded by the sum of the individual probabilities of all the different events, right? So we can actually upper bound it like this. Okay, so that's our upper bound for, yes?
The first quality, at least one query returns a false positive. That also
Yes, because I'm assuming here that this is a query to an empty query range. Okay, so that's good. So as you can see, this becomes kind of useless if you have a large R, a large query range. Now, recall that this epsilon in something like a quotient filter or a Bloom filter, this is just proportional to 2 to the power of minus f, where f might be the fingerprint size if we're using a quotient filter or a Cuckoo filter. So now you might ask the question, suppose that I wanted to cancel out this R term, right? I could just use longer fingerprints, right, to kind of cancel that out, right? And so you might ask, how many extra bits would we need to have the false positive rate of just a regular filter, assuming that we have range filters of size R? By how much longer would your fingerprints need to be? Log R, correct. Because if you take that log R, right, and we kind of add that to the exponent here, right, these two cancel out. Okay. So overall, what's the story here so far? Either our FPR is higher by a factor of R, or we can use log R extra bits per entry. But overall, this is a worse trade. This is kind of a worse trade-off than we had before, and the trade-off gets worse the bigger R is. And also note that even if we wanted to apply this trick, we have to know what R actually is, right? So this does not, even if we wanted to do this, this does not allow us to support truly variable length queries because we have to commit to a given R up front, and that's going to bound the maximal range query size that we can issue. Okay, so it makes sense to everybody? So here's kind of a summary of our problem so far. It's kind of our problem analysis. So these are the problem. This is what we're trying to solve when we construct a range filter. So far we saw that we can achieve a query cost of OR, but right, how close to constant time can we make this? How good can we make the false positive rate be? And can we really get rid of that R term and make the false positive rate independent of the range query size? Can we support variable length keys rather than just fixed length keys? Right. And finally, we also want to be able to support variable length queries. Right. So, and ideally, we want to achieve all of these goals at the same time. And hopefully now you can see that this is highly non-trivial. Okay. Good. Oh, and in addition to that, we have yet another goal, which is for general purpose applications, we also want to be dynamic. So we want to support dynamic insertions, deletes, expansions, and contractions. Okay, so as I said before, this has been a hot topic of research over the past 10 years or so, even more. It actually kind of started with a theory paper in SODA in 2014, which actually gives a lower bound for this problem and also a theoretical construction, even though it could be implemented, but it hasn't actually been implemented in this paper. Then we have SURF coming up in 2018, and after that, right, things start to kick, and there are a few papers coming out every year on this topic. So we're going to cover in this class 3 of these papers. So SURF, which is the first practical range filter, which is not the best solution, but pretty good for the time and kind of instructive to still explore. And then 2 other papers that are from our lab. And here's kind of the rough story of how things evolve across these. So we begin with SURF, and SURF does allow you to support variable length keys and queries. However, it doesn't actually provide you with much of a false positive rate guarantee at all. So we're going to see why. So it might be good for some cases, but it's hard to argue that it's good for any workload or even for common workloads. We'll see that the query speed here, right, not constant time, but it's actually going to be dependent on the length of the keys. And it's not dynamic. Okay, we'll then move on to Memento Filter, which does not support variable length keys and queries, right? So in some sense, it's less general purpose than SURF, right? But it does actually do a good job in all the other metrics, right? So this actually does give you a very robust false positive rate, constant time queries, and it's dynamic. But then, this leaves something to be desired because it's not fully general purpose, right? So that's what's being addressed in Diva. So Diva is kind of a middle ground. And that gives you variable length keys and queries. False positive rate is semi-robust, so not good for any conceivable workload, but pretty good for common workloads, provably. Query speed is somewhere in between, log of the length of keys as opposed to constant or the full length of keys. And it's dynamic, right? So as usual, we can't get the best of all worlds, but we can get pretty good compromises. Okay, and I should say both of these are projects done by Navid, and Navid is actually going to present these. So I'm going to present SURF, and then I'll hand it over to Navid. Okay, so here's SURF. And let's see how this one works. Hopefully, I can do this in 15 minutes. So this paper proposes to actually just create a trie of all the keys in the set that you're trying to represent. Not a full trie. So, we'll see what it does. But first of all, just, for illustration purposes, here is a trie representing the following 3 keys, right? I guess you've all seen this before, right? Okay, good. So the fan out there using is 1 byte. It's nice, byte aligned. Okay, so what are the problems of, right? So we could already use, so we could just use a trie, right, for this problem to tell us whether a given range exists or not. What's the problem though? 2 problems.
So how compact can you store this and why does she?
Yep, all of these are valid. So you're correct about both. Here, I guess I'm referring more to space, and I'm referring to 2 manifestations of the problems of space. But you're right about pointer tracing as well. The first issue is this is storing the full keys, right? So that's going to take up a lot of space. The second problem is that, the pointers from each node to the next node also take up a lot of space and will, in practice, probably inflate your whole space consumption by a factor of 2 or 3 or more. Okay, so here is how we're going to get around those two issues. For the first one, we're going to do that using by truncating the trie. So this is going to become an approximate trie. And secondly, we're going to show how to encode this trie succinctly without the use of pointers. And, as usual, we're going to be using kind of rank and select data structures for this. Okay, so that's the outline. But the truncation thing, so the truncation thing is conceptually quite simple. Let's choose some points towards the end of the trie, right? And just chop all nodes beyond that point. Now, we're going to keep at least one unique byte for each key, though, right? So you can kind of see that here. So each one of these keys, we still store one unique byte that allows us to differentiate between all existing keys. So for instance, truncation here would not be permitted because that would no longer be, allow us to, kind of store one unique item for each key. Okay. So now that we're truncating the trie and the trie is becoming approximate, what does that do? Well, now we can get false positives, right? So now we're getting into filter land. So for instance, suppose you're querying for the following keyword, sigmetrics. This is now going to lead to a false positive, even though this is not a key that we actually inserted, right? But it just happens to match a prefix of some existing key. Okay, and note that we can actually control where the cutoff point of truncation is to control the false positive rate, right? So if we're willing to spend more space, we could do the truncation, subsequent layers to prevent these false positives. Here, I'm, including one extra layer. Now there's an O here, and now note that this query is no longer false positive. This is now a negative. Okay. So how do range queries work in general? We might search for a given query range. And if we see that a given query range does not match any existing prefix in the trie, we know that it's a negative. So that's good. However, if you have a range query that matches, one or more existing prefixes, right, then you get a false positive. All righty. So now note that, okay. Can somebody start to see why this thing doesn't really give us a robust false positive rate guarantee? And articulate why?
Depending on where you truncate, if the key lengths from that point are much farther, then you could have insanely high false positive rates, and it depends on how they're concentrated.
Yeah.
Like if they're all concentrated with the prefix that you've kind of truncated, and now they're all they match the prefix, but they're all way longer than that, you're going to get a lot of false positives.
Right.
And
right.
If the key length kind of is close to where you truncate, and I guess there isn't much prefix matching, these won't get.
Yeah. So I think all that's good. Does somebody else want to comment on this? Yeah.
More of an observation, but basically it returns true whenever you reach the leaf node, as long as you reach the leaf node. And I guess when you do a range query, as long as you end exactly at the leaf node and whatever that range, however big that is, it will always return false positive.
Right. Right.
That range is kind of unbounded, you can have 8 and 7 and you greater.
Yeah. Excellent. The core point is that, the query workload might be, kind of pretty close to the actual keys, right? And you could definitely have a situation, where, perhaps everything that the user is querying for are existing prefixes, right? You can't really help that. It's just a thing that might happen, right? And this means, and these things are actually quite common, right? Imagine that you have a particular distribution of keys, it becomes very likely that the user is aware of what the data distribution is and is going to query for things that are not too outlandish values, right? Imagine that you're searching for, the heights of people, right? I mean, as a user, you know what the range of reasonable heights for human beings is, right? So you're likely to query for things that actually exist. So this is why there isn't really a guarantee here, and this is called a correlated workload. Okay, so a correlated workload means that your query workload is correlated to the actual keys, and such workloads, which are actually pretty common, you don't really get a good guarantee. Okay, for point queries, we can actually alleviate this problem, right? So for point queries, you could actually store a small hash here at the edge of each key, but you can't generally do this for range queries. Okay, so that's the summary. Does it support variable length keys and queries? Yes, it's a try. Does it provide a robust false positive guarantee? Not really, because you can have a situation of a correlated workload where the queries are very similar and just happen to always match existing prefixes. This makes the filter essentially useless. What is a query speed? Query speed is going to be proportional to the length of keys, essentially, right? Because you have to traverse the trie. And is it dynamic? Not really, right? It's kind of stored as compactly as possible. So you can't really, once you've constructed this, it's static. Okay, so that's the end of that part. And now we're going to be addressing these handicaps with the Memento filter and Diva. And Naveed, feel free to come. Okay. So I hope this works.
All right, sorry about that. Okay, I'm going to lay out some assumptions first. This is going to tie back into the discussion at the beginning of the lecture, where, okay. So I'm going to assume that our universe is a finite universe. So basically, your keys are fixed length, and I'm going to assume our range query lengths are bounded. So I'm not going to be concerned with those variable length concerns that we talked about at the beginning. Those are going to be addressed by Diva, which is the next thing that we're going to talk about. Okay, given those two assumptions, the key idea in Memento filter is to partition your universe. So you have this universe here, which is a line, you have a bunch of points on it. We're simply just going to split this into a bunch of partitions, each of size 2 to the log of r. So it's going to be the size that's the smallest power of 2 that's at least as big as r. Okay. Now, if you do this, you'll see that queries can intersect at most 2 of these partitions simultaneously. So your query is either fully included in a single partition, or it's going to cross a partition boundary, and it's going to overlap with 2 partitions. Okay. So in this scenario, I guess the sort of observation is that you can kind of localize the query to these partitions and answer like a simpler problem in that local partition exactly. So what do I mean by this? I mean, if you have knowledge of the offsets of each key from the start of the partition in each partition, then you're able to answer that localized query by comparing the endpoints and those keys. Okay. All right. So that's sort of the rough idea and the direction we're going to go. First, I'm going to explain to you how this partitioning and offset computation goes. So let's take this key, blue key in the middle, as an example. I'm going to look at its binary representation, and I'm going to split this binary representation into 2 parts. It's going to give me a prefix and a suffix, which I'm going to call the memento from now on. The prefix is in some sense the partition index that the key is a part of. So we can think of the universe partitions as being numbered from 0 to n for some big N. And the partition index is basically just the prefix itself, right? So in this case, the prefix of that key k is going to be simply 2. And the memento is going to give you the offset from the start of that partition. If you think about this for a bit, you'll see that, yeah, that just holds. Okay. And again, because our partitions were of size 2 to the log r, your memento only has to be of size log r bits. Okay. So the idea then is to, given these partitions and the partition indices and the offsets, we're simply going to encode them in a quotient filter. So let's see how the storage layout is going to look like in the end.
So, okay, consider this middle partition first. To encode this guy, I'm first going to list out the offsets, the mementos that I care about. So the first key is going to have an offset of 5, a memento of 5. For example, the second one is going to have a memento of 7, and the last one is going to be 8. Okay. Now, what I'm going to do is I'm going to look at the partition index, which is 2 in this case. I'm going to hash that to go to a run in the quotient filter. Then I'm going to store a fingerprint for that partition index. So in this case, I'm going to store a fingerprint, which is a hash of the value 2. Okay. Finally, I'm going to store that list of mementos that I derived at the beginning right after that fingerprint. Okay. So this is basically the, I guess, base structure that I care about, which is a fingerprint plus a bunch of offsets. Okay. And I'm going to call this guy a keepsake box from now on. Okay, so given these keepsake boxes, I'm going to illustrate for you guys how you can support inserts, deletes, and queries real quick. So in this figure right here, you have your quotient filter. The big boxes represent clusters. The hatched boxes in those big boxes are going to be runs. And the white boxes inside of those hatched boxes are going to be your keepsake boxes. Okay. So when you get an insert, the idea is you just find the keepsake box that has a matching fingerprint in its corresponding run, or if there isn't any, you just create one, and you add your memento to it, the memento of that new key to it. So for example, if you add that blue key in the second partition over there, that's going to enlarge or shrink it's going to enlarge one of your keepsake boxes, which also, because you're working with a quotient filter, is going to shift some slots in the cluster to maintain the semantics of your quotient filter. Okay, so that's how you handle inserts. Deletes are very similar. When you just find the keepsake box with the same fingerprint and you remove the memento you're planning on deleting. This may potentially exhaust the keepsake box, so it might become empty, at which point you just remove the entire thing and destroy it. Okay, so as an example, if you remove that guy over there, one of your runs is going to shrink, like so. And then, you're going to shift stuff to the left to maintain the compact encoding of your quotient filter. All right. So do insertions and deletions make sense? Like roughly speaking. All right, cool. So let's briefly talk about queries as well. Again, as before, because of how we do our partitioning of the universe, any range query you take is going to intersect with most 2 partitions. So the idea here is to find the keepsake boxes of those overlapping partitions. So in this case, I have these 2 partitions that I care about. I'm going to hash their partition indices. They're going to map me to a bunch of keepsake boxes, this one on the left and that one on the right. And I just have to read those keepsake boxes and see what mementos they have in them, the offsets. And then again, I just compare those mementos with the endpoints of the queries. Because I know what the endpoints of the queries are exactly, and because I know what partitions I'm working with, given the information of the offsets, I can sort of reconstruct exactly what's going on inside of each one of these partitions, right? And given that reconstruction, I can do this comparison and check for inclusion. Does that make sense? All right, cool.
Questions at this point, though?
Oh, yeah.
Does this not also have the problem that we need to predefine a R which is bigger than all of the things?
Yes, this does have that problem. That's a problem that we're going to address in the next range filter. Okay, anything else? Yeah.
So if you have a bunch of inserts,
Mhm.
do you have to rebin these buckets? Ones?
No. So your partitioning is fixed from the very beginning that you create the filter. And yeah, you don't change. That's actually an interesting, I guess, future work direction where you might want to have varying partitionings, have a more balanced structure. But yeah, that's not what it's doing right now. Anything else? All right, cool. So now you might be thinking, well, those mementos that I'm storing are basically giving me a lossless encoding of what's going on inside of each partition, right? So where do false positives come into play? And the answer to that question is, well, I'm hashing the partition indices, right? So false positives come into play when you mistake two partitions with each other, not what's going on inside of each partition. So you might have two partitions that have the same fingerprints, and because they have the same fingerprint, your query is gonna give a false positive. All right. Cool. So that's how Memento Filter is. Oh yeah, go ahead.
So you have a collision with two partitions. Is it mementos of both of them go into the same thing?
Yeah, the memento lists are merged. Good question. Any other confusions? All right. So now that we know how this structure works at a high level, let's talk about how you might encode these keepsake boxes. So I guess the core issue here is that your runs are no longer just a bunch of fingerprints as you would expect in a normal quotient filter. They're basically storing a bunch of keepsake boxes which are more complex than a normal fingerprint, right? So you need to have some sort of mechanism to be able to delimit these guys and to decode them unambiguously. Okay. Now, one simple solution to this problem could be using a special character as a delimiting character. So after each keepsake box, you have a delimiting slot that stores some special character you're not going to use, and that's going to tell you where the keepsake box ends. Why is this not a good idea? Oh yeah.
You have to state that character else for the point.
Yeah, that's one thing. You can't use that character anywhere else. And the other issue is that this is actually quite memory expensive. So, for each keepsake box, you basically have this padding that you're never going to use. So it's going to be a lot of overhead in terms of memory. Okay. So in some sense, what we're trying to shoot for is a self-delimiting encoding, where the keepsake boxes themselves are enough to delimit each other. And if you have such a thing, it's basically minimizing the metadata overhead. So you're getting the thing that you want. Right? And to achieve this, we're going to enforce this invariance right here. So we're going to store the keepsake boxes in a run in increasing order of their fingerprints. So as you scan a run from left to right, like this run, for example, you expect to see larger and larger fingerprints as you go by. Okay. We're going to see that, okay, so if you enforce this invariant, the moment you see a fingerprint that's bigger, that's already indicating to you that you've finished the keepsake box right now, and you're seeing a new keepsake box, right? Because you have an increase. So that's sort of like the main utility of this invariant, but it's also nice because it's going to allow us to come up with a more space-efficient encoding for some special cases. We'll see this in a sec. Okay. Before I talk about how the encoding actually goes, let me say a bit of stuff about how each slot is structured in this quotient filter. It's quite simple. I'm going to simply split each slot into a memento part, into a fingerprint part, and a memento part. The fingerprint part is going to store fingerprint, and the memento part is going to store some memento. That's it. Okay. So given this slot structure, now we're ready to talk about the keepsake box encoding. Oh yeah.
So is it like you have like each slot has fingerprint and memento? Each memento you store has that fingerprint next to it, or do you have like a single fingerprint in all the mementos after this?
That's a very good segue to what I'm going to talk about next. So yeah, some of my encodings are going to have, each memento is going to have its own fingerprint, and some of them are going to have a single fingerprint and just a list of mementos. Okay. All right, so that was a great segue. Let me just jump right in. If you want to encode a partition that has a single thing inside of it, like this key K, you're just going to use a single slot. You're going to store the fingerprint of that partition in that slot, and then you're going to put the memento of that key right next to that fingerprint. This is going to be your encoding. Okay. So as an example, you can have something like this going on in your filter. And again, to illustrate how this is self-delimiting, if the next slot in the run has a bigger fingerprint, so like you have a fingerprint of all ones versus the fingerprints 1 0 1 1 0, that's indicating to you that the keepsake box is finished. So, this is sort of like the delimiter that you can use to figure out where the thing starts and ends, right? So that's the case of size 1. If you have 2 things in your keepsake box, it's similar. You're just going to use 2 slots. You're going to store a duplicate of the fingerprint in both slots of the partition's fingerprint. And you're going to store the smaller memento in the first slot and the bigger memento in the second. Okay? And yeah, that's basically just the encoding. Just to see an example again, you have the same fingerprint repeated twice. You have 2 mementos, and then if you have something, the next slot in the run, if it has a bigger fingerprint, then that's already gonna be the delimiter that you're gonna work with. Does that make sense? Yeah.
You guarantee that the fingerprints are always bigger than the length of the memento?
So that's very common in practice. So most of the time, most of the configurations you're going to have your filter being used in are going to have longer fingerprints than mementos. But this also works if you have shorter fingerprints than mementos. So
If they're equal size, then you have a problem.
why is it a problem?
Because if they're equal size, you could confuse maybe the next like entry in the memento be the next fingerprint, right?
No. So the difference is I'm addressing my filter on a slot by slot basis. And I'm partitioning each slot into 2 things. So the way I scan the run is on a slot by slot basis. When I look at a slot, I know exactly what part is the fingerprint and what part is the memento. Cool. Okay. All right. So that's the first 2 cases. These are basically the cases where you're just repeating the fingerprint. The last case, which is probably the more interesting case, is where you have a bunch of things inside of your partition and you want to encode all of these. Okay? Conceptually, you could just repeat this encoding and store the fingerprint multiple times, but as your friend mentioned, you can cut down on the encoding length by storing the fingerprint only once. And the way we're going to do this is, by doing this type of an encoding here. So I'm going to store the fingerprint of the partition in the first slot. Then I'm going to follow that up with a slot that has a 0 fingerprint. Okay. So this is going to create a decreasing order of fingerprints in my run. And the 0 fingerprint is that decreasing order is going to act as an escape sequence, right? So the moment I see a fingerprint that's decreasing, I know I'm in this special encoding case. So I'm going to parse the keepsake box differently. Okay. So yeah, so that's how we set up the fingerprint bits in some sense. Now, we're going to store the mementos like so. I'm going to store the maximum memento near the fingerprint and the minimum memento near the 0 fingerprint. This is kind of weird, but this is just going to let us access the max and min mementos quickly, which is going to help us out during queries. We'll see this in a second. Okay. And whatever's left, we're going to encode in a sorted list. So if you have L things in your partition, you're going to write down a length field, which describes L minus 2. Because, the max and min you've already stored near the fingerprints. And the remaining L minus 2 mementos you're going to store in the keepsake, in the sorted list. And just as an implementation detail, this length field itself is using log-r bits. Doesn't really matter how many bits you use, but yeah, that's just what we use in practice. Okay. And the rest of the mementos you're just going to sequence in a misaligned fashion across your slots. So as you can see, M3 is part of M3 is stored in the 3rd slot and part of it is stored in the 4th. Okay. So yeah, that's basically how you encode this. So as a summary, if you have 1 or 2 things in your keepsake box, you're going to use either 1 or 2 slots and duplicate the fingerprints. And if you have more than 3 things in your partition, then you're going to use this sorted list encoding. I'm also reiterating here, the first 2 cases, you're going to delimit by using the fingerprint order invariant. So if you see the next thing has a bigger fingerprint, that's delimiting your keepsake box. And the third case is delimited by the length field itself. So once you see that you have a list of mementos, the length field is already describing how many slots you're using for your sorted list right here. So the slot immediately after that has to be a different run. You can also use this to skip over that keepsake box and have fast access. All right, all clear? Yeah.
Is it possible for a fingerprint to be all zero?
Yes, that's a very good point. So the way the filter handles this in the third case is it's going to revert to using this encoding right here. So it's going to duplicate the 0 fingerprint multiple times per memento.
You have L copies of the slots.
Yeah. So it's going to be more expensive in terms of space if that happens, but fingerprints are uniform, so you expect to not see that happen a lot. All right. Any other confusions, questions? Yeah.
So just on I guess the conceptual proofing, the keepsake box is per each partition.
Yes.
Okay. And so, even more of a basic question: the universe to begin with, and all the keys that are inserted under it, are they sorted in any order, or do you hash it and then insert it into a certain partition? Is that how the design works?
So the partitioning is done in the intrinsic ordering of the universe itself. So if your universe is like integers, for example, if you take the prefix, that's already obeying the intrinsic ordering of the integers. That's what I'm assuming is what's going on. So there's no hashing going on top of that. Once you have the partitioning, then you hash the partition numbers, and then you get like the mapping to the quotient filter. Does that make sense?
Yeah.
Okay, sounds good. Anything else? All right. Okay. So let's again cycle back to see how range queries are done. I'm going to focus mostly on the case where your keepsake boxes are long, because this is really where the, I guess, interesting stuff is going to happen. The other two cases are handled similarly. Okay, so we have two cases for our range queries. They're either going to intersect a single partition, or they're going to intersect two partitions. Okay. In the first case, when you have a single partition, the idea is to find the predecessor of the right endpoint of the range. So the predecessor is like the rightmost key that's to the left of the right endpoint. This guy is in some sense the most probable key that's going to be in the range. If that guy is in the range, then the answer to your query is a positive. And if it's not, then the answer to the query is a negative. Okay. So the way we're going to find this is, well, we're just going to take into account the max and min, and then we're going to binary search over the sorted list. If you find the predecessor during binary search, then you're done. If you don't find it, you check the max and min. Okay, make sense? All right. The case where you have two partitions is a bit more interesting in the sense that now you're going to see why storing the max and min near the fingerprints is going to be useful. Okay, so here we actually care about two partitions, and each one of those partitions is going to have its own keepsake box. And the idea is that the maximum of the first partition and the minimum of the second partition are the guys who are most probable candidates for being in the range. So if those guys aren't in the range, then you're good. Otherwise, then it's a problem. If those guys aren't in the range, your answer is a negative, and if they are, the answer is a positive. Okay. And the only thing you need to do to check these guys is to check the maximum memento near the fingerprint in the first keepsake box and the minimum memento near the 0 fingerprint in the second. You don't need to do any binary searches anymore. Okay. So yeah, that's for range queries. Point queries can also be handled in this way. It's quite similar. So you care about a single partition here. You just find its corresponding keepsake box, and you check all of the mementos for something that's equal to the query. So again, you check the max and min, and you do a binary search. Okay. All right, so that's it for, oh, you have a,
Oh, how do you find the partition first place, for the point where,
right. So, if you recall at I mentioned that the partition index is defined by the prefix of the key.
Right.
So if you have an integer, the lower order bits, the lower order log R bits is going to give you the memento, and the prefix is going to give you the index of the partition. Right. So given a query, you can take the query key and split it into a prefix and a memento. That prefix is going to give you the partition.
right? You have it for slicers, like the key split between prefix and memento.
Yes, exactly. Yeah.
It's basically, you use that binary representation to get you the prefix, which is the index to the partition.
Yes. Yes.
So that's what there.
Yes. Yes. Yeah.
Does that also mean the universe, regardless if there are, filled values or not, it just has to be like gigantic?
Yeah. So in some sense, the construction doesn't really care how big the universe is. It only cares about how big your range queries are. Because the prefix itself is never really stored anywhere. You're just hashing it and storing a hash of it. You're only storing the mementos explicitly in some sense. And the size of the memento is determined by the range query length. Is that correct?
Yeah.
Yeah, so in some sense, the universe size itself doesn't really matter that much. You only care about the range query size. Yeah.
Get false positives if the partition index is 5.
Yes, yes, exactly. Any other questions? Yeah.
I think you're about to get to this, but I think in the slide that you shared said that the worst case time was 01, but like clearly is a binary search.
Yeah, I'm gonna get to this real quick. All right, so let's talk about the analysis. So I'm gonna denote by L the average number of keys and non-empty partitions. So you have a bunch of non-empty. Okay, this again ties back to the size of the universe thing. You have this gigantic universe. It's partitioned into a bunch of small partitions. Most of those partitions are empty. Some of them are non-empty. L is going to be the average number of keys in the non-empty. Okay. I'm also going to refer by alpha to the load factor, the filter's load factor, which is going to be the ratio of the number of keys to the number of slots. Okay. And this again ties back to your question. False positives only happen because of fingerprint collisions of the partitions. Now, given this observation, you can derive the following ugly FPR expression right here. So let me dissect this for you guys. So M over N is the bits per entry budget, because M is like the total number of bits you have, and N is the number of keys you have. Alpha times that is going to give you the affordable slot size in your filter. Okay. For each slot, you had a log R portion that was storing the mementos, and you have a metadata overhead of 2.125 if you're using a rank and select quotient filter. So if you subtract these off, that expression inside of the parentheses is going to give you the fingerprint length. And 2 to the negative of that is going to give you the collision probability of the partitions. So you just have to multiply that by the average number of keepsake boxes you check per query. And that's gonna be like this. So alpha over L, you can verify. I haven't really spelled it out here, but you can verify that it's the average number of keepsake boxes per slot or per run. And we multiply that by 2 because in the worst case, you check 2 partitions for a range query. So that's going to give you the overall false positive rate. Okay, so that's the false positive rate. The cluster size, well, now, I guess, yeah, you might be wondering, well, we're storing a bunch of things consecutively here in the quotient filter. That might be bad for the cluster size and the filter's performance, well, because having sequential storage in the filter is going to be bad for hashing sometimes. But it turns out it's not too bad. Your cluster size is going to remain at O of L, which is sort of like the best you can hope for. But the proof of this is a bit complicated. If you're interested, you can take a look at the paper. It isn't too long, but it's just, it's gonna take a while. All right, so given that expected cluster size, that automatically translates to an insertion and deletion cost of O of L, because in the worst case, for an insertion or deletion, you have to shift the entire cluster. So that's going to be your insertion and deletion. For range queries, as mentioned, because we're doing a binary search, our cost is actually O of 1 plus log L. But here, L is the average number of non-empty partitions. So again, the 1 is the cost of finding the run and skipping over a bunch of keepsake boxes, which are constant in expectation. And the log of L is just the cost of the binary search on average. Okay. So L turns out to be very close to a constant in many, well, very close to 1 actually in many real world applications. But if it isn't, the nice thing about the range queries is that you're still doing just a single random cache miss. You do a random cache miss for getting to the run, and then every single other access you make is just sequential right after that. So accesses in that sense are going to be quite fast, and your bottleneck is really like the single cache miss you incur at the beginning. Okay, so it kind of goes back to your cost model. If you're counting CPU operations, then yes, it's going to be O of log L. But if you're counting cache misses, which are, I guess, in some sense what you care about, you get 1. Okay. And the case where your range query intersects 2 partitions is handled similarly. Here, you just don't have the binary search, so your cost is going to be constant, but you have 2 random cache misses instead of 1, which is still good, but it's not 1. All right. All clear? Cool. So that's it for Memento. Again, it has its own problems. We're not supporting variable length keys, and this is mainly because you're splitting the keys into prefixes and mementos, and this quickly becomes ambiguous if you have variable length keys, right? So if you have these 2 keys right here, you would like to have your mementos be of the same size because of how we encode things in the quotient filter. But then again, you would like your mementos to you would like to use your mementos to compare the keys, right? So if you define your mementos like this, they correspond to bits of different levels of significance. So you can't really use them to compare the keys themselves, right? If you want to compare the keys, you might want to work with something like this, but then your mementos are going to be variable length, which is going to pose some issues with your encoding inside of the quotient filter. So that's one issue that doesn't seem to be reconcilable. And the other issue is the assumption of the bounded range query length. We would like to ideally not have any of these assumptions. Oh yeah, and this one also happens because you're working with fixed length mementos and you want to only check 2 partitions at most. Okay. It's also kind of fun because the moment you try to support variable length queries, as you mentioned, you're also forced to support arbitrary range queries because any range you take in the context of variable length queries is going to have infinite keys in it. So you're kind of forced to solve these 2 problems at the same time. Okay. So this begs the question of, can we design a robust and dynamic range filter that resolves these issues? And interestingly, the answer is no. The reason for this is actually the theory paper that Neve mentioned at the very beginning. So they prove that if you want to design a robust range filter, if you want to design a robust range filter, then you need the log of R over epsilon plus some constant number of bits per key in terms of memory, at least. Okay. So again, R is the max range size and epsilon is your false positive ring. Okay. So in the case of Memento, you can verify that your fingerprints are of size 1 plus log of 1 over epsilon. And your mementos by definition, are of size log of R. Okay? So these 2 together kind of match the lower bound of the theorem over there. So in some sense, we're happy because Memento is doing the best thing that's possible. You can't really do anything better physically. But in some sense, we're unhappy because we want to support variable length queries and we want to support variable length keys. So what do we do? Is there any way out? And turns out, the way out is to not support robustness, is to support a more relaxed version of robustness, which we call semi-robustness. And this refers to basically guaranteeing an FPR of epsilon for common data sets, not every single data set. So we're disregarding, in some sense, the worst case ones. So this is really what you want in practice, right? You're rarely going to see worst case workloads and data sets in practice. So it makes sense to try to have semi-robustness instead. Okay, so with that, we design Diva, which is the first range filter to provide you semi-robustness, dynamicity, high processing speed, and variable length keys and queries. Okay. So let's jump right in and see an overview of this. So the structure has two cases. So it has a static case and a dynamic case. They work pretty much in the same way, but the dynamic case has some extra quirks and all that we have to handle. I'm not going to get into that today. We're going to mostly focus on the static case. Okay. But the idea in both of them is to learn the dataset's distribution in some way. So the way we're going to do this is as follows. So I'm going to take the set of sorted keys. So I'm going to take all of my keys, I'm going to sort them. This is going to give me some sort of list. Okay. Then I'm going to sample every teeth key. So these gray boxes are going to be my samples. And each two consecutive samples are going to be T apart. And you can think of T as a parameter around 1024-ish. It's like a big-ish parameter. So yeah, you're gonna get N over T samples, which are gonna be which is a much smaller set compared to the set of all keys that you have in your data set. Okay. We're gonna store these N over T samples in a small trie. And again, the trie is small because you have way less samples than keys. Yeah, proportionally. Okay. So you get this trie, right? The trie is encoding the samples exactly. So you're storing like the full keys in your trie, the full sample keys. Then you have to somehow store whatever's left in your data structure. Well, what we're going to do is we're going to sketch those keys that are in between approximately. So we're going to come up with an approximate representation, and we're going to store them in data structures we like to call infix stores. So again, here is like, if these two samples if you take your first two samples, these are going to correspond to these two paths in your trie. All of the keys that are in between these two samples are going to be summarized in this data structure that's going to be stored in between those samples inside of the trie. Okay. So does the overall structure make sense? Okay. So let's have a quick look at how this structure is going to let you handle range queries. So if you get a range query like this one, the first thing you do is you check if a sample in the trie is in the range. And again, because the sample trie is storing the exact samples and you have the exact representations of the queries, you can check if this thing exists or not without any approximation. So if you do have a sample that's inside of the range, then you get a true positive. Okay. So these types of queries are all handled, right? And again, well, you can also have like multiple samples inside of the range. As soon as you have just a single sample inside of the range, then you get a true positive. If that doesn't happen, then your range lies in between two samples, or which is pretty much the same as inside of an infix store. Okay. In this case, you're simply going to query the infix store. This is really where you might get false positives because you were sketching the keys in between the samples. So that's where the, I guess, approximateness and all that kind of stuff and filter land comes into play. All right. Okay. So so I'm first going to describe how you can sketch the keys, and then I'm going to describe the data structure that you're going to use to store these sketches. All right, so let's consider the first two samples, A and B. Now let's take the set of keys that are in between A and B. Okay? I'm going to take one of these keys in between, and I'm going to show you how you can use the representations of the samples themselves to come up with a nice sketch of the key that's in between. Okay, so let's take A and B. In general, they can have different lengths, but for now, for simplicity, let's assume they have the same length. And oh yeah, in this figure, I'm assuming that the x-axis is representing lexical ordering. So the sample A is going to be smaller lexically than the sample B. And the y-axis is going to represent the significance of the bits in the samples. So the upper you are, the more significant bits you're looking at, and the lower you are, the less significant the bits you're looking at. Okay. And let's take a key that's in between A and B. Okay. And for concreteness, let's just suppose that our samples A and B are these strings right here. All right. So, right. So because this key is sandwiched in between the samples A and B, you can think of A as the predecessor of the key and B as the successor of the key in some sense. If you look at the ordering of all of these guys. So the way we're going to sketch the key in the middle is we're first going to compute the longest common prefix of the predecessor and the successor. So in this particular example, the first 5 bits of these keys comprise the longest common prefix of these predecessor and successor guys. Because the predecessor is smaller lexically than the successor, the bit that immediately follows the longest common prefix has to be 0, and in the successor it has to be 1. Okay. The key observation here is that because we're storing the predecessor and successor inside of the trie, this part of I should have mentioned this. The longest common prefix of the predecessor and successor must also show up as a prefix of the key in between, because otherwise the key wouldn't be in between these guys. Okay. All right, so the key observation is we're already encoding this information inside of the trie itself. So it doesn't make sense to encode this anywhere in the sketch of the key. So we're just going to truncate it and remove it. Okay. From what's left, we're going to take log of t over epsilon many bits. Again, t was the number of, oh yeah, sorry, you would.
No, scratch.
Okay. From what's left, we're going to take the most significant log of t over epsilon bits. So t is the number of keys that are in between 2 samples, or like the spacing between the samples. And the parameter epsilon is going to be your target false positive rate. We're going to keep those, and we're going to throw away whatever's left from the key. This is going to be the sketch that we're going to use, and we're going to call it an infix because, you know, it's something in the middle of the key. It's not a prefix and it's not a suffix. It's an infix. Okay. Does that procedure make sense? Okay. So let's talk about what properties these infixes have. The first one is quite nice, actually. So if you have a smooth distribution over your data set, so here I'm showing you a distribution. The x-axis is the keys in your data set, and the y-axis is your cumulative distribution function through CDF. And it's sort of like a smooth curve. The observation is that when you take a bunch of samples from your data set, the keys in between the samples, I'm not sure if you can see this, but we have blue lines as our samples here in the figure. The keys in between these guys are going to be approximately uniformly distributed. Okay, so you can see this visually by drawing lines between these samples right here. So you can see that, you know, for illustration sakes, this doesn't really fit the exact CDF underneath, but you can kind of see that each one of these lines is sort of like a close approximation of how the CDF is behaving underneath. Okay? So you can sort of assume that the keys in between the samples are uniform and roll with it. Okay. Now, because the actual keys underneath are uniform in between the samples, then if you remove the longest common prefix and just take the infix that's going to follow that, that infix itself is also going to be uniformly distributed. So your infixes are going to be like, you know, they're going to be uniform, and they're nice because they are also order preserving. So if you have 2 infixes, because the infixes were parts of the keys themselves, if you have two infixes, A and B, such that infix A was smaller than infix B, that means that, you know, key A, which infix A came from, had to also be smaller than key B, right? So putting these two together, in some sense, the infix is behaving like an order preserving hash. Does that part make sense? Yeah.
Allow for least significant bits, then could they not be equal, even if it is better than
They may turn out to be, yeah. But okay, the model we're sort of analyzing the structure in is we're assuming that your keys are coming independently from a underlying distribution that's well behaved. If that happens, because you're taking samples, okay, if that's the case, because you're taking samples, it's kind of unlikely that your infixes are the same, but it could happen. You're right. Any other points? All right. Okay, so the infix behaves like a order preserving hash. And because of how we sized it, you have a total of T over epsilon possible hash values, okay, for each infix store. So again, you have T things in between two specific samples, and each one of, we're gonna hash them based on, well, it's not really hashing, but we're gonna sketch them, and we're gonna get a smaller universe of size T over epsilon. Now, again, well, if you think about this for a bit, you'll see that I'm kind of lying a bit. You need some technical tweaks to actually make this happen in all cases. You can take a look at the paper if you're interested to see the details, but this is roughly in spirit what's going on. Okay. All right, so let's jump into how an infix store works. Before that, any confusions about what an infix might be doing or its properties? Okay. So let's see how you can encode these infixes in your infix store. So an infix store is a structure that's very similar to a ranking select quotient filter. I guess the first point of similarity comes into play because you're doing quotienting. So in an infix store, what's going on is, in this figure again, the more significant bits are shown on top and the less significant bits are shown below. An infix store applies quotienting to all of its infixes. So it's going to take each infix and it's going to split it into a quotient, a log T bit quotient, and it's the rest, which is going to be a log of 1 over epsilon bit string, is going to be your remainder. Okay, so the quotient is going to be used to map your infix to a slot in your infix store, because your infix store, because each infix store is going to store T infixes. You can imagine it as a filter that has T slots. So having a quotient of length log T is enough to address those T slots. Okay, and in those slots, you're going to store the remainders themselves, which are going to act as your fingerprints. Because your infixes are uniform, it's going to be nice and all that. Okay, so let's see an example of how this is going to work. Let's suppose you have an infix 1, like so. The way the infix store is going to encode this is it's going to employ a occupied bitmap, similar to a ranking select quotient filter. The occupied bitmap is going to encode what quotients we've inserted until now into the filter. So in this example, your infix 1 has a quotient of 0, so it maps to the 0th bit in the occupied bitmap, and it's going to turn it into a 1. Okay, so that's how you store the quotient itself. You also need some way of storing the remainders, which for that, you're going to use an array of slots. And you're simply going to store the remainder of infix 1 in the first slot that you find empty. Okay. Now, the next infix you take, which is going to be like a bigger infix, I'm assuming that you're constructing the infix store from smallest infix by inserting the smallest infix all the way up to the biggest infix. So the next infix you take, well, in this example in particular, it has a quotient of 2. So it's going to map to the second bit in the occupied bitmap. It's going to set that bit to 1. And then similarly, it's going to store its remainder in the next empty slot in the array. And if you have an infix 3, well, this one also has a quotient of 2. So it doesn't change the occupied bitmap, and it stores the remainder in the slots. Okay. Now you can observe that this procedure is basically storing the remainders of. Okay. As a result of this procedure, the remainders that share the same quotient are stored contiguously in your array of slots. So they form runs, as you're familiar with. Right. So in this particular example, the first infix was the only one that had a remainder of 0, a quotient of 0. So it's forming a run of size 1. And the next two infixes had the same quotient of 2. So they form a run of size 2, which is this blue one over here. And if you continue this, you'll get a bunch of runs like so, which you can represent using this line. And you're almost done, basically, by doing this. The only thing that you need now is some way of being able to tell where runs begin and end. And for that, you just use a run-ins bitmap, similar to a quotient filter. So for each slot that ends a run, you're going to store a 1, and for all other slots, you're going to store a 0. And that's it. All good? Yeah?
Very similar to the Ellis funnels.
Yeah, it's also very similar to Elias fauna encoding. Yeah.
Why don't you just use?
So you can use Elias fauna encoding. I guess it's going to look very similar to this in the end.
Doesn't support dynamicity.
Yeah, that's going to be a problem. So if you do this, then you can imagine over provisioning the slots in the dynamic case and kind of like adding space in between. That's going to give you the ability to support dynamicity. But with Elias fauna, you know, everything is packed. It's going to be hard to handle. Any other questions? Okay, so that's the general structure. This way of laying out this data is kind of nice in the sense that you now have matching 1 bits. So every 1 bit in the occupied bitmap, well, it's basically telling you that you have an infix with that quotient, and that's automatically telling you that you must also have a run corresponding to that quotient, right? So there must be a corresponding 1 bit in the run-ins bitmap. So you get a matching like so. Tells you, you know, for any 1 bit in the occupied bitmap, you have a matching 1 bit in the run-ins bitmap. And it turns out these ones have equal rank. So the first one in the occupied bitmap matches the first one in the run-ins bitmap. The second one in the occupied bitmap matches the second one in the run-ins bitmap, and so on and so forth. Okay. So you can use rank and select primitives to, you know, traverse this matching. And because you have efficient CPU implementations for rank and select, this is going to be quite fast. Okay. So that's the structure in its generality. Let's talk about now range queries. Okay. So when you only do a range query over an infix store when both of your query endpoints happen to land in that infix store, right? If that happens, what we're going to do is we're going to sketch those endpoint keys. And that's going to give us 2 infixes, a left infix and a right infix. So now your range query over strings has now been converted into a range query over infixes. Okay. And in this scenario, you have 2 cases. In the first case, well, you have 2 cases. Either the quotients of your endpoints are the same or they're different. Okay. So let's start with the case where your quotients are the same. So take this example. Your left endpoint and your right endpoint in this scenario both have a quotient of 2, right? So they're going to map to this bit in the occupied bit. Okay. Now, if this bit were 0, that means that no infix exists that is in between these endpoints, right? So your query can terminate and return a negative at that. But here in this example, we see a 1 in the occupied bitmap. So we have to further go down and traverse the corresponding run to see if anything exists in between these guys. Okay, so we do rank and select, we go to the run end, and we have to scan the run from right to left for inclusion between the endpoints. So I have a bunch of remainders right here. And the thing that I'm looking for is a remainder that's in between the remainders of the left and right endpoints. And as you can see, because these remainders are, my left endpoint has a value of 3 and my right endpoint has a value of 5. And the stuff that I'm storing here are 2 and 6. So none of them are in between. So my Fourier returns a negative. Okay. So that's the case when your quotients are the same. What happens when your quotients are different? So this case is also going to be split into 2 subcases. In the first subcase, in this example, your left endpoint has a quotient of 2 and your right endpoint has a quotient of 4. In the first subcase, you happen to have a 1 bit that's strictly in between these 2 endpoints, the quotients of these 2 endpoints, right? In that case, this basically means that you have a run that's strictly in between your endpoints. And because your infixes were order preserving, this implies that your query is a true positive. This you can tell now because it's a true positive, so you never make a mistake on this query. And so let's assume this doesn't happen. And you have your endpoints and your quotients like this, and you don't have a 1 bit strictly in between. So what you have in between is a 0. In this scenario, you have to expand and go further down and see what's inside of the runs to be able to answer the query. Okay. So in this case, we're gonna use the matching and do some rank and select to get to the runs. And again, this is going to look very similar to what we did with Memento. What's actually going to matter is the maximum remainder in the left run that you find and the minimum remainder in the right run, because those are the most probable candidates of being inside of the range. Okay. So those are going to be these 2 values over here. And if you compare them with the left and right endpoints, you see that the max endpoint in the left run is smaller than the remainder of the left endpoint, and the minimum remainder in the second run is bigger than the remainder of the right endpoint. So none of them are included in between the range query, and that will give you a negative. Yeah.
Why is it necessarily just max and min? Like, could the remainder be closer to the min of one range on the left side, and on the right side, shouldn't the remainder be closer to the max? In
Right.
this case,
I see.
if the remainder was like all zeros on the left side.
Right.
And or on the right side, suppose the remainder was all ones.
Right. Okay. So this goes back to the, I guess, if I understood your question correctly, this goes back to the order preserving nature of the infixes. So if I have 2 runs, right, the one that's corresponding to the smaller quotient, in some sense, they kind of correspond to partitions in space. So the one that corresponds to the smaller quotient, your range query is going to start somewhere in the middle-ish, and it's going to span and go beyond the end of the partition, right? In such a scenario, the thing that you care about most is the rightmost infix that can potentially be in that range, right? Does that make sense, sort of? I'm kind of hand waving here.
Yeah.
But that translates to the max, and the analogous thing happens on the other side, where you care about the minimum. All good? Okay. So yeah, that's how Diva works. Again, we saw 2 interesting properties here. We saw that if you have an infix that's strictly in between the endpoints, because of the order preserving nature of the infixes, you get a true positive. So this implies that you only get a false positive if you have collisions with the endpoints themselves, right? And this kind of already implies that you can support range queries of any length, because you don't care really what's going on inside of the range. You only care if you have a collision with the endpoints. So regardless of range size, your accuracy is never going to deteriorate. You only care about the endpoints, roughly speaking. Okay. Does that track? Does that make sense? Okay. So let's do a quick analysis of this, and that would be it. So we're going to suppose in our analysis, and sort of like the scenario where that Diva is designed for is the scenario where your keys come independently from a well-behaved distribution. So as an example, the normal distribution is a well-behaved distribution. It has this type of a CDF, which is quite uniform and which is quite smooth and nice and all that. A CDF that looks like this isn't really a well-behaved distribution. And you really don't expect to see this in data sets that often in practice. You don't expect to see a skippy distribution many times. Okay. Most of the time, you expect to see distributions in practice that are mixtures of normals. Like many natural distributions are going to have, they're going to be like multimodal distributions, like they're going to have multiple peaks, and each one of those peaks you can model as a single normal distribution. They're going to be like a mix of these guys. For these ones, the analysis holds. Yeah.
Yes, I was actually thinking this one was brought up. So I guess the intuition for why it works well with uniform distribution, right, where the CDF is straight line.
Yeah.
Is because the infix is at the end of the day kind of like stacking the prefix of your your key.
Yeah.
And if your key is uniformly distributed versus it's like there's a sudden spike, right, in a certain sample set, and you take only the prefix, you're gonna have a lot of the differentiator is actually at the least significant bits, and those are completely chunked, right?
Yeah.
So that's why. But if you look at a normal distribution, like the slope in which it suddenly increases despite the CDF, and you take the sample, the 1024 sample at that point, which also ends up in a similar position where you have stripped off the significant bits that could have differentiated these keys, right?
That could happen, but the observation is that that's very unlikely. And the reason for that is, well, if you think about it, because we're taking samples, and samples are like the teeth key each among the data set, each teeth key. If you think about it, what's actually going to happen at the end is you're going to take way more samples from the spike than from the rest of the distribution, right?
Yeah, that's true. Yeah.
So because you're taking way more samples from the spike, the longest common prefix that you're ignoring is going to be longer and longer. So the thing that you're actually going to store is a lesser significant amount, a lesser significant portion of the keys. Does that make sense?
Yeah, so it's like it's every 1024 keys. It's not every 1024.
Yeah, exactly. It's not every 1024 along the key space.
Right.
It's every 1024 keys. So in some sense, the samples are kind of like horizontal lines instead of vertical lines. Yeah.
Sir,
Sorry.
what about insert?
So I didn't get into those today. Turns out insertions actually work. The idea is roughly when you get an insert, you flip a coin. With some probability, you're going to store it as a sample, and with some probability, you're going to store it as an infix. And it sort of does the same thing. Cool. Okay. So under these assumptions, we're also going to define L to be the average key length. If you do this, then you can show that the FBR is this expression over here. So let us dissect it. M over N is going to be the bits per key budget. So the 2 over here is the metadata overhead for the infix store, because for each slot, you're storing a occupied bit and a run-ins bit. And the L over T is the memory overhead of the trie itself, right? So because you're storing a T fraction of the entire data set, and each key has an average length of L. So you're gonna get a per key overhead of L over T, which is actually quite small because T was huge. So this entire expression inside of the parentheses is going to be your remainder size, or your fingerprint size in this case. Because the infixes were uniform, 2 to the negative that is going to give you the collision probability. That multiplied by 2 is going to give you the probability of a false positive for a range query, because a range query has 2 endpoints. Check. All right. Now, the nice thing you can notice that this expression is independent of range size. So this gives you the nice independent, variable length queries and variable length keys. Okay, so that's that. Now let's talk about the time complexity of this thing. So the time complexity is highly dependent on what type of trie you use. I'm not going to get into this too much. We're going to use what is known as a Y-fast trie. It's like a cache efficient trie or whatever. That's going to give you O of log L access and update time, where L is the length of the key. So it's kind of like an interesting dynamic that's going on. So you get O of log L time for traversing the trie over here. And well, the n-fix stores were constant time, so the n-fix stores aren't gonna be the bottleneck in your processing time. So you're gonna get a overall cost of log of L for both inserts, deletes, and queries. So yeah, that's pretty much it. If you enjoy these types of problems, I highly encourage you to reach out. We would love to have you involved in research. And yeah, hope to see you soon.